Hey, 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 we're ready for some more vector fun. So what we're going to do now is we're just going to try some applications of some stuff that we already know and maybe figure a little bit more out, give you a little bit more definitions and terms, some different things that we're going to use when we're dealing with complex numbers, vectors, and eventually polar coordinates. All right, so here we go. First thing we're going to do is we're going to consider 2 plus 3i and 6 plus I, and we're going to find the distance. All right, so we've got these 2 points. Find the distance between these. Now you can do it on an Argand diagram if you want. You can draw a picture. So let's do that first, and then we do it mathematically because we can. So here we go, Argand diagram. So in the real, I got 6, 1, 2, 3, 4, 5, 6, and then 1 positive in the imaginary. And then I got 2 in the real and 1, 2, 3 in the imaginary. So I see that if I create a triangle here, there will be a distance of 2 squared and 4 squared. So I go 2 squared plus 4 squared equals c squared, and I get 4 plus 16, and therefore c equals the square root of 20. All right, and so what I want us to do is now do this mathematically as well, just to show that we can. So the distance from, let's just call these A and B. So we say AB is equal to, and we go the square root of x. So we go 2 minus 6 squared. So x1 minus x2, or x2 minus x1. It really don't matter, does it? Plus 3 minus 1 squared. And so I did a minus b. It's just the length. It doesn't really matter. It doesn't really have a direction. So from there we should get ab equals the square root of negative 4 squared plus 2 squared, and that gives us exactly the same thing. Alright, so you can do it with a picture, you can do it without a picture, whichever you want, whatever beats your fancy. Alright, let's go ahead and try another type of question. So let's consider we've got a Argand diagram. Here we go, Argand, with a vector z. Okay, so let's not do one quite that fancy. Let's go just over here. So this represents vector z. Now, if I want iz, the question is, what are the transformations required to go from z to iz? Alright, so let's think about this. If z is represented by a plus ib, right, with your real part and your imaginary part, if I take that and multiply it by I, so iz equals ai plus I times ib, note that I times I is negative 1, so I end up with ai minus b. So if I compare these two, alright, so it looks like what has happened. It looks like the a and b have switched. Alright, now remember that is a reflection in the xy plane. So the a and b have switched. Your a went over there, your b went over here, and the b is now negative of what it was. Alright, so let's just use this example right here where I had my real was 3 and my imaginary was 2. So if I switch those, right, so ai minus b, so b will now be 2 and then 3, and then it's gonna, the b is gonna flip over to the other side, right? That's my real part. So instead of positive 2 here, it's gonna be negative 2. So it'll be negative 2, 3, and you'll notice that that right there, my friends, right, because now I have negative b. B was positive 2, so now I got negative b for my real part, and I got a positive 3 still for my imaginary part, and you'll notice that that is a rotation of a 90-degree angle, or pi over 2. So it's pi over 2. Now that's counterclockwise. There you go, and that's the transformation. A rotation counterclockwise of pi over 2. Alright, so hopefully that makes sense, and we're going to move on from there. We're going to try something else. Alright, So the next thing we're going to say is, all right, we've already talked about this vector here, and we gave a special name to the length. So we're going to take this and we say, okay, well, I got a vector here, vector z, and we already said that the length of z is the modulus. Okay, and you see it this way, you also sometimes you may see mod z, right? Just like that, and it could be in parentheses or it could not be. It doesn't matter if it's a z. So that's the same thing, and that those all represent the length. Okay, but it would be awfully convenient if I had some way of identifying this angle as well. All right, so we are going to identify the angle, okay, not just any angle, but the angle between the vector and the positive x-axis, or in other words, the positive real axis, and we are going to define this as the argument. Okay, so the argument, or arg z, is the angle between z and the positive x-axis. Now, that means that this right here, let me write this out. We go z as a function of arg z equals theta. Now, there's a problem with this. This is a relation. This right here ain't a function. Why? Why is that not a function? Pause the video, see if you can figure it out. Alright, well, we're back. I hope you paused it and thought about that a little bit. Well, the reason why this is not a function is because that theta could be theta. But it could also be 2 pi plus theta. It could also be 4 pi plus theta. And so there are several possible values here for this y value. You put z in, you put this vector in, but your theta could be several different angles. And that's the important thing to recognize, because it will keep going around and around and around and around forever and ever. Alright, so this is not a function. There are several angles that could go on there. And let's go ahead and let's maybe look at one more question before we finish video number 2 here. Okay? So here we go. I'm just going to write it right here. So we're going to go pause. There you go. Find all possible values of r and theta such that z1 equals z2 if the modulus of z1 equals r squared, the argument of z1 equals 3 theta, the modulus of z2 equals 5r minus 6, and the argument of z2 equals theta plus pi, where r is greater than or equal to 0. Alright, so let's go ahead and work through this one. Now, as we're working through this one, there's a lot of stuff going on here, but the main thing is that z1 and z2 are equal.
So in other words, because this looks quite messy, it really isn't. Because if the vectors are the same, then that means their lengths are the same. And so we can go r squared equals 5r minus 6. And then we just subtract the 5r and add the 6. And I got r squared minus 5r plus 6 equals 0. And then I got r minus 2. R minus 3 equals 0. And so I have my values for r. R equals 2 or 3. And those are both positive, because it says r has to be greater than or equal to 0. So that's easy enough. And so now what I do is I'm going to look at the other ones. Okay, so same thing is we're going to say, well, I don't really want to set these equal to each other, because they don't have to be equal to each other. You know what I'm saying? Because this one could be, 30 degrees, and this could be 390 degrees, because it's 30 plus 360. So what I need to do actually is just say that the difference between the angles, so 3 theta minus theta plus pi, is equal to 2 pi k. So what that does is it says the difference between these two needs to be at least 2 pi, or some multiple of that, including 0. It could be 0, but it could also be 2 pi, and that would be okay. And negative 2 pi is okay too, because k can be positive or negative integers. Alright, so from there, we go ahead and just do it. And so we go 3 theta minus theta minus pi equals 2 pi k. And we add the pi to both sides and subtract the theta, and we get 2 theta equals pi k. Solve, and I get theta equals pi over 2k. So therefore, plus or minus pi over 2, and so on. And so, oh, I probably shouldn't do that. That was not a good idea. Hold on, wait. We're going to add the pi. When we add the pi, we'll have 2 theta equals 2 pi k plus pi. I can't put those together. What? Those aren't like terms. Okay, so divide by 2. And so now I got theta equals pi k plus pi. That looks better. I like how that looks. Okay, there we go. So theta equals plus or minus pi over 2, and then plus a pi, so that would be 3 pi over 2 plus or minus, and on and on forever. Alright, so there you go. We got all our thetas, we got all our r's, and we've answered the question, which looked quite complex, but really isn't all that bad, except for this one little thing right here where we got to make sure that it's 2 pi, not that they're equal. Alright, okay, very good. That's this video.